You'll have to forgive some things during this lecture, namely cat noises. Two of the cats got into a bit of a scuffle beforehand, so one of them is locked up with me. So you'll hear a fair amount of meowing. I hope you don't find it too distressing. Hello, students. So, this begins the final chapter of these notes. And here's the main goal of this final chapter. Power series. So you may remember, in the course of Calc 2, you introduced such ideas like that e to the x is the same thing as the sum k equals 0 to infinity of x to the k divided by k factorial. So what we're going to start studying is things like that. And, well, obviously, what does that mean? That should mean the limit as n goes to infinity of the sum from k equals 0 up to n of x to the k divided by k factorial. So that means we need to study the limit of a sequence, but every term of that sequence is a function. So it behooves us then to try to determine what does it mean for a sequence of functions to converge. But before we can even do that, we need to figure out what the heck a sequence of functions is. What is a sequence of functions? So let's explore that. So the idea behind a sequence of numbers converging to some limiting number L is that as the parameter n gets large, we can make x sub n as close as we want to L. Right? That's all it means. What about sequences of functions? Can we study the limits of them? We need to if we want to figure out power series. And we need to figure out what it means for a sequence of functions to get close to some limiting function. There are lots of different powerful definitions of the limit of a sequence of functions, and they're all different. They're suited for different things. I'll introduce two. So, first things first, what is a sequence of functions? Well, that's easy enough. Let u be a subset of R for each n in n. Let f sub n from u to R be a function. Then, if you regard the lot of them, one of them for each natural number n, that's what a sequence of functions is. Alternately, well, a sequence of functions is just a rule that takes a number n and gives you a function. Well, you can think of that as being a rule that takes a number n and an element of the domain and returns a number. So you can think of a sequence of functions by the rule f from n across the domain of these functions to R via the rule that takes f of n, comma, x, so n the natural number, x an element of u, and returns f sub n of x. So there are just two ways of thinking about these. So if I give you a sequence of functions, then what should it mean for that sequence of functions to converge to that limit? So a function f from u to R is called the pointwise limit of a sequence of functions f sub n if, well, here's the so-called pointwise limit definition. For all x, the sequence of real numbers f sub n of x converges to f of x. That's all. So it's called the pointwise limit because we're saying that for each point in the domain, the sequence of outputs converges. So two different points in the domain don't know about each other under this definition. They just have to converge to this limiting function. So expanding the definition of convergence, right, I know what this means. I know what it means for a sequence of real numbers to converge. So let's just expand that definition. So if I expand that, I get a fully quantified version of this definition. We say that a sequence of functions f sub n from u to R converges pointwise to some limiting function f from u to R if, for all x in u, and maybe I'll write this in Greek to emphasize that I mean this. For all x in u, for all epsilon greater than 0, there exists some choice of big N such that for all little n bigger than big N, the absolute value of f sub n of x minus the alleged limit is less than epsilon. So check it out. So if you wanted to prove that a sequence of functions converges pointwise, then you would start by saying let x be in U, let epsilon be bigger than 0, then you would need to come up with a choice of big N. On what things can that big N depend? Well, it can depend on everything that comes before it. Big N can depend on x and epsilon. So the reason I'm saying things this way is because this should give you memories of the definition of uniform convergence. So the idea of not uniform convergence, uniform continuity. So in the definition of continuity, let's remind ourselves of that really quickly. F is continuous on U means for every p in U, for every epsilon bigger than 0, there exists a choice of delta such that for all x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. So you looked at this and you said, what can that delta depend on? Well, it can depend on p, and it can depend on epsilon. We uniformized it, this definition, by saying that the delta has to be the same for every x value, uniformly continuous if for every epsilon greater than 0, sorry about that, there exists a choice of delta such that greater than 0. For all x and p in the domain U, if absolute x minus p is less than delta, then absolute value of f of x minus f of p less than epsilon. So the difference between the two is this delta can depend on the place where you're checking for continuity. This delta cannot. Similarly, this big N can depend on where you're checking for convergence. That big N can depend on the choice of input x. Well, let's write a new definition, and we'll explain why it's a good idea to do. By uniformizing the N, let's rewrite this so this N depends only on epsilon, not on x. And, well, you know exactly what I'm going to do. How did we make it so that delta didn't depend on p? Well, we just declared delta delta before p. Well, I'll just change this definition so the big N is declared after the x. Before the x. X comes after n. So here it is, definition. Let f sub n be a sequence of functions. For another function, f from u to r, we say that f is the uniform limit of this sequence of functions. And I'm going to try to do my best today especially to be specific, indicate that a sequence of functions is actually a sequence by putting parentheses around it. If for all epsilon bigger than 0 there exists a big N such that for all little n bigger than big N, if little n is bigger than big N, then for all x in U, absolute value of f sub n of x minus f of x is less than epsilon. So that's the same definition as above, right? The only difference is the choice of the statement for all x was moved to the end instead of the beginning. That was the only difference. On what can this n depend? Well, it can depend on things that come before it. So there's n. There exists some n. Here's a for all epsilon, and that's the only thing we know about beforehand. N can depend on epsilon only, not on x. And of course not on little n, because otherwise you could just say, well, I'm going to take, well, it can't. So there's a good reason to uniformize the definition of limits, and it's similar to the reason that it was good to uniformize the definition of continuity. When we have uniform continuity, we can do things like take limits at every limit point. We'll want to do something similar with sequences of functions. We'll want to say, well, I know something is true for every term in this sequence of functions. When do I know that the same is true for the limit? And the following example will tell you that if you just have a pointwise convergent sequence of functions, then the limit can be a bad function. And what do I mean by bad function? By bad, I mean not continuous. So let's see this example. So proposition 4.1.4. For every n in Blackboard bold n, let's define f sub n from 0, 1 to r, closed interval 0 to 1 to r, by the rule f sub n of x is equal to x to the n. So now f sub n is a sequence of functions. I will define f of x to be the function that is 0 when x is not equal to 1, and is 1 when x is equal to 1. I claim f sub n converges pointwise to f. I claim that for every number c smaller than 1, f sub n converges uniformly to f on at least the closed interval from 0 to c, so as long as you avoid 1. And f sub n does not converge uniformly to f on the closed interval from 0 to 1. Before we even give the proof of the first item, let's see some pictures. So here we see the graph of y equals x squared, y equals x cubed, y equals x to the 4th, x to the 10th, x to the 20th, x to the 30th, x to the 40th, x to the 70th, x to the 90th, x to the 11th. And here we see this alleged limiting function f of x. So let's just stare at that for a second. Does it look like for every fixed input, x, the output x to the n is getting close to this limiting function? Yeah, if I take any input that's smaller than, that's between 0 and 1, not equal to 1, then it looks like as I iterate, the y values are getting closer and closer to 0. So yeah, it sure looks like the limit of f sub n of x for each fixed x is 0, except for 1. When you plug in 1, you get 1, 1. You always get 1. 1 to the n is always equal to 1. So yeah, the limit is 1. So it sure seems to be the case. And we see already that this limiting function is not continuous. So let's go ahead, and we have intuitively the result, but let's also see what the proof is. So let's define f sub n of x. So proof. Let's set f sub n by the rule f sub n of x is equal to x to the n. Let's define f of x by the rule that f of x is equal to 0 when x is less than 1 and is 1 when x is equal to 1. First, we will prove the pointwise convergence claim. Let's consider any little x in big X and any epsilon bigger than 0. If x is equal to 1, then we'll get some choice of big N. Maybe we'll even see what that is informally. So x is equal to 1. We eventually want the absolute value of f sub n of x minus f of x less than epsilon. And, well, what is f sub n of x? Well, it's going to be 1 to the n. F of x, by definition, is 1. That's always equal to 0. Yeah, that's less than epsilon. It looks like I don't care what big N is. When x is equal to 1, I will let big N be, don't care, 1. If x is between strictly less than 1, then let's see what we need. So I'll eventually want f sub n of x minus f of x to be less than epsilon. So this is scratch walk, right? What is f sub n of x? It's x to the n. F of x is defined to be 0. That is x to the n. I guess absolute value bears for now, but x is positive, so x to the n is positive. So that's just x to the n. I need that to be less than epsilon. Well, do you think you could, like, well, let's see. So x to the n, x is a number that's between 0 and 1, so that's less than x to the big N. Well, do you think you could set that equal to epsilon and solve? Sure, I think so. I guess you would get n equal to the log base x of epsilon. Of course, there's a problem there. That's what works when x is bigger than 0. Maybe we need a separate proof when x is equal to 0. When x is equal to 0, x to the n is just 0. Again, you have a constant sequence, so I think big N equals 1 will do the trick. So let's allow for that in our proof. If x equals 1 or x equals 0, then I'll set big N to be 1. If x is strictly between 0 and 1, I will set big N to be the log base x of epsilon. I will now assume that little n is bigger than big N. And, well, I'll deal with the two special cases first. If x is equal to 1, then f sub n of x minus f of x is equal to the absolute value of 1 to the n minus 1. But that's 1 minus 1, which is 0, is less than epsilon. Great. Similarly, if x is equal to 0, then absolute value of f sub n of x minus f of x is 0 to the n minus 0, which is still 0, is less than epsilon. In both of those cases, we get what we need. In the case that x is properly between 0 and 1, then the absolute value of f sub n of x minus f of x is equal to, by the definition of f sub n of x and f of x, absolute value of f sub n of x minus f of x is x to the n minus 0 is just x to the n. Since x is a number that is strictly between 0 and 1, and little n is bigger than big N, I see that this is less than x to the big N. And that is equal to x to the log base x of epsilon by our choice of big N. And that is equal to epsilon. So thus, between all of these three cases, we see that for every x and every epsilon, there exists some big N, such that if little n is bigger than big N, then the absolute value of f sub n of x minus f of x is less than epsilon, as we claimed. And we'll notice something. Our choice of big N definitely depends on the choice of x. For 1 and 0, we just chose 1. When x is a number strictly between 0 and 1, n was the log base x of epsilon, definitely depends on x. Definitely depends on epsilon. So this proves, thus, f sub n converges pointwise to f on 0, 1. So let's do the next prove the uniform convergence claim. So this is claim 2. So fix some c in between 0 and 1, not equal to 1. So 0 is less than or equal to c is less than 1. In fact, let's change it to this, because I want 0 to c to actually be an interval. So c had better be bigger than 0. So what will I do? So maybe I'll write down the want to show. So fix some c between 0 and 1. What is it that I want to show? I want to show f sub n converges uniformly to f on 0 to c. That is, I need to show that for every epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N, and for all x in 0 to c, absolute value of f sub n of x minus f of x is less than epsilon. So let's try to do that. So again, do some scratch walk off to the side. So the goal is eventually f sub n of x minus f of x is less than epsilon. Well, I'm definitely avoiding x equal to 1, because this x is just going to be in 0 to c, and 1 is not less than or equal to c, because c is less than 1. So that means f sub n of x is x to the n f of x is 0. So that's what my goal really is. But let's see, I know that x is in 0 to c. So this bit is less than or equal to just c to the n. And I need that to be less than epsilon. Well, now I'll use the fact that little n is bigger than big N. That's less than or equal to c. No, strictly less than c to the big N. Well, I can set that equal to epsilon and solve. It looks like log base c of epsilon is a good choice of big N. And notice, there are no x's here. This is independent of x. It depends on c, but it's allowed to because the function itself depends on c. You'll have to forgive the cat noises again. So let's now actually come up with a proof. Consider any epsilon bigger than 0. I need to prove something is true for all epsilon bigger than 0, so I'll consider any epsilon bigger than 0. I've already figured out what big N should be. Big N should be this. So I'll take that choice of big N. Big N be the log base c of epsilon. Consider any little n bigger than big N and any x in the closed interval from 0 to c. Then, absolute value of f sub n of x minus f of x is equal to x to the n minus 0. That's best, so it simplifies down to just x to the n. Well, no, x is less than or equal to c, isn't it? So, since 0 is less than or equal to x is less than or equal to c, which in turn is less than 1, this is less than or equal to c to the n, which is less than c to the big N. But c to the big N is c to the log base c of epsilon, since big N is equal to the log base c of epsilon. But that simplifies just down to epsilon. So let's see what we did. We have proven that for every epsilon bigger than 0, because we started by considering any epsilon bigger than 0, there exists some big N, namely that, such that for any little n bigger than big N and any x in the interval from 0 to c, the difference between f sub n of x and f of x is less than c. I was worried it was less than or equal to, which would have been a problem. Nice. So, the final thing to prove is that f sub n does not converge uniformly to f on the interval from 0 to 1. So let's do some logical calculus, figure out what we want to show. So what is it that we want to show? We want to show not f sub n converges uniformly to f on 0 to 1. So what does that mean? i.e., we want to show not for all epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N and for all x in U, absolute value of f sub n of x minus f of x is less than epsilon. So there's what we need to negate. It's easy to negate though, i.e., we need to prove there exists an epsilon bigger than 0. So we get to come up with an epsilon, but that epsilon doesn't depend on anything. It will be a constant. There exists an epsilon bigger than 0 such that for all big N, there exists a little n bigger than big N, and there exists an x in U such that the negation of that conclusion, such that this inequality does not happen. Absolute value of f sub n of x minus f of x is bigger than or equal to epsilon. So we need to prove that there exists an epsilon bigger than 0 such that for every choice of big N, there exists a choice of little n bigger than big N, and x in 0, 1, such that absolute value of f sub n of x minus f of x bigger than or equal to epsilon. All right, so in order to see what's going on, I've zoomed in on f sub 100, f sub 200, and f sub 300 on the interval from 0.95 to 1. So looking in that interval, can you find an x value, an input, so that this output is far away from f of x? And remember, f of x is 0. Can you find an input where this output is far away from that output? Yeah, it looks like if you take inputs that are getting really, really close to 1, that distance is approximately 1. In particular, it's bigger than a half. So, it sure looks like epsilon equal to anything between 0 and 1 will walk. So let's take epsilon to be 1/2. That seems like the simplest thing to do. And now, well, let's see if we can't do the walk. Let's figure out, find an x value for which the absolute value of f sub n of x minus f of x is bigger than or equal to 1/2. And certainly an x value of 1 won't walk. When x is 1, f sub n of x is f of x. So we'll only be interested in x values that are not equal to 1. So under that case, we will get f sub n of x to be x to the n minus 0. We'll want that to be bigger than or equal to 1/2. So, continuing on, we'll need x to the n. Absolute value pairs don't matter, right? Everything's positive. Bigger than or equal to 1/2. Well, how about if we just go equal to? That would also make us happy, right? If it's equal to, then it's also bigger than or equal to. That's easy to solve for x. I'll take x to be the nth root of 1/2. Nice. That should do the trick. Let's just do a quick sanity check. If I take the nth root of 1/2, do I get a number between 0 and 1? Well, yeah, I can't get anything bigger than 1. If the nth root were bigger than 1, then the number itself would have to be bigger than 1. And the nth root of a positive is a positive. So let's do this. So consider any big N. I'll let n be, well, I didn't say anything about n, did I? But I will take x to be the nth root of 1/2. And apparently it didn't matter what n was, but little n has to be bigger than big N. So come up with your favorite choice of a little n bigger than big N. Maybe I'll use big N plus 1. So, or maybe if you want to be really careful, right, because big N isn't always a natural number, maybe you'll want to take the ceiling. So, let's now walk it. So that was this item right here. Under these choice of epsilon, big N, little n, and x, let's see what we get. Well, we get f sub n of x minus f of x equal to absolute value of x to the n minus 0 equal to just x to the n. This in turn is equal to the nth root of 1/2 raised to the power n. Oh, but that's just 1/2, right? Oh, but 1/2 is certainly bigger than or equal to epsilon because our trace of epsilon was 1/2. So, let's see what we've done. I claim that this proves that there exists some epsilon bigger than 0. There's the trace of epsilon bigger than 0, such that no matter what big N you choose, for any n, there exists some little n bigger than big N, namely big N plus 1, or the ceiling of big N plus 1 if you want to be careful. And some x, namely that x, maybe you used a different one, nth root of 1/2, such that f sub n of x minus f of x, which negates the definition of uniform convergence. So this limit, this function f, is not the uniform limit of f sub n, even though it is the pointwise limit. And now I'll come back to these questions that I was trying to use to motivate. So what do you think? If f sub n is continuous on all n, and f is the pointwise limit of f sub n, does it follow that f is continuous? Think for a second. Okay, in class there would be a poll, but I can't possibly do that when I pre-record things, so I don't know. Leave a comment in the YouTube video of yes or no. Anyway, so you thought about it for a second. Let's see. This sequence f sub n equal to x to the n is definitely continuous, but f sub n converges pointwise to f of x equal to 0 when x is less than 0, 1 when x is less than 1, 1 when x is equal to 1. But this function f is not continuous. So this is a counterexample, isn't it? It is not true. Version 1b. If f sub n is continuous for all n, and f is the uniform limit of f sub n, then does it follow that f is continuous? We certainly don't have a proof of it right now, but at the very least, the one example that we've done, right, well, kind of two examples, right? We proved that if you only look at the closed interval from 0 to c, well, certainly the limit is continuous there. The limit is just 0. So maybe that's evidence that yes, it does follow. Suppose that the limit is as x approaches c of f sub n of x is equal to L sub n, and that the limit of L sub n as n goes to infinity is L. Does it follow that the limit as x approaches c of f of x is equal to L? Said another way, if we take the limit as n goes to infinity of the limit as x goes to c of f sub n of x, is that always the same as the limit as x goes, to c of the limit as n goes to infinity of f sub n of x? Can we reverse the order of limits? And that's something that's super tempting to say yes to, right? You really want things to commute. But we see that we can't. Let's take this same example. Take that same example. If we take the limit as n goes to infinity of the limit as x approaches 1, maybe for emphasis I'll say 1 from below, of x to the n, let's see what we get. What's the limit as x goes to 1? It's just 1. A limit as x goes to 1 of x to the n. That converges to 1. So I'll see the limit as n goes to infinity of 1, which is 1. On the other hand, if we take the limit as x converges to 1 from below of the limit as n goes to infinity of x to the n, I'll see, well, the limit as x converges to 1 from below. Remember, when I take the limit as x goes to 1, I don't care about what happens when x is equal to 1. So I'll get this limiting function f of x, but f of x for every x value that's less than 1 is 0. So that's the limit as x approaches 1 from below of 0. That's just 0. And you can't get much more different than that. I guess you could say plus infinity, well, whatever. So are they the same? No. So there's a counterexample. It turns out, though, that if we replace pointwise limit with uniform limit, the result turns out to be yes. Wonderful. So I think that will conclude this particular recording session. I'll see you in just a little bit, and we'll start by doing something pretty light. I'll just give an example of a sequence that does converge uniformly. Cool. See you in a moment.